Hello, welcome back to Unit 8, Stoichiometry and the Mole. Today's topic is 8.5, mole relationships, and the aim for today is to calculate mole ratios from a chemical equation. So chemical equations, if we look at the equation, some of the information that we can get is qualitative, which means what elements are in the formula, and quantitative, which is how much of each element. So qualitative describes the qualities of the equation, while quantitative describes how much, or numbers. And coefficients, we've been talking about these for the last couple days, are used to balance the equation. So balancing the equation means that you have to make sure that mass is conserved on both the reactant side and the product side. So you have to make sure that the numbers are balanced out, and that's what the coefficients are used to do. So these set up a ratio of the compounds in a reaction. So it tells you how many molecules of each element there are, or each substance, and also how many moles of each that there are. So mole ratios, when we're given this type of equation, okay, this tells us here that we have 2 moles of C2H6 plus 7 moles of O2, or oxygen, produces 4 moles of carbon dioxide and 6 moles of water. So our ratio here is 2 moles and 7 moles produces 4 and 6. So we can use this to then figure out if you had more or less of one substance, how many you would have of the others, because it turns out to be just a ratio. So we start off with 2 for our C2H6, right? 7 for oxygen, and then on our product side we have 4 carbon dioxide and 6 water. This is exactly what is in the formula, the original equation. So now if we change any of the numbers of moles, we can figure out what we would end up with. So for example, if we change this to 4, okay, if we have 4 moles, now we also then can figure out what we would have for each other part of the equation. So if we started with 2 and we go to 4, this was multiplied by 2. So we would have to multiply every other part by 2 to figure out what would be produced. Okay, so the ratio has to be the same for every mole within that equation. If we change the first amount to 1, okay, so now we're going to say we just have 1 mole of C2H6. Now we've gone from 2 to 1, so that's half, right? We now have half. So this is multiplied by 0.5. Okay, so then you can multiply 7. Half of 7 is 3.5. Half of 4 is 2. And half of 6 is 3. So if we had 8, let's say now we have 8 moles of C2H6. What is the relationship between 2 and 8? Okay, so you could see from 2 to 8 you are multiplying by 4. Right, so this is multiplied by 4. So now if we started with 7 and we now want to go change this to the same ratio, we need to multiply each part by 4. So 7 times 4, you would end up with 28 moles of oxygen. 4 times 4, we end up with 16 moles of carbon dioxide produced. And 6 times 4 gives us 24 moles of water produced. Okay, so changing the amount of moles in any one part of our equation, we can figure out, based on the ratio, how much every other part would be. So how many moles of water will be produced from the complete combustion of 3 moles of ethane according to the following equation? So here's our equation. We're starting here with 2 moles of ethane, 7 moles of oxygen, so the same formula we just were looking at, 4 moles of carbon dioxide, and 6 moles of water. So these are the ratios given in this balanced equation. So now it's saying if we start off with 3 moles of ethane, okay, so here we're going to have 3 instead. How do we get from 2 to 3? Okay, so you could set this up as a proportion, okay, or you can recognize that 2 times 1.5 will give us 3. Okay, so 2 times 1.5, I'm going to show you both ways in case whichever way works better for you, would give you 3. So we can multiply each of these by 1.5. Okay, but actually the question is asking us how many moles of water. So we want to know what the water will end up to be. So if you multiply 6 times 1.5. Put that in your calculator, and you get 9 moles of water. Okay, so that's one way to do it, to look for the relationship between what you're starting with and what you're ending with, and then multiply any other part of the formula by that same number. You also could set it up with, as a proportion. So if we start off with 2 moles of ethane and 6 moles of water, if we have 3 moles of ethane, how many would we end up with H2O? X is the number of moles of H2O. And then you can cross multiply. So we end up with, we're just going to keep the numbers here. So we end up with 2 times X equals 3 times 6, which is 18. Divide out the 2, and X equals 9, which is what we got right here. So if you see the relationship, you can just do it straight out, or you could set up a proportion and multiply it out and find the same answer. Some sample regions questions. Given the reaction, 4 aluminum solid plus 3 oxygen gas produces 2 aluminum oxide solid. What is the minimum number of moles of oxygen gas required to produce 1 mole of aluminum oxide? Okay, so our relationship here, we have 4 aluminum plus 3 O2 produces 2 aluminum oxide. So now it's saying if we want to produce 1 mole of aluminum oxide, so we want this to be 1. How do we get from 2 to 1? You divide 2, or you could say you multiply it by 0.5, right? It's half. So half of 2 is 1, right? So this is divided by, or multiplied by 0.5. Okay, so half of 2, so 2 times 0.5 gives you 1 aluminum oxide. So now if we want to see how much oxygen we would need to produce that, we would also multiply 3 by 0.5. Okay, 3 times 0.5, or half of 3, would be 1.5 moles of O2. That is one way to do it. The other way is if you set up your proportion. Next regions question. Given the reaction, 2 KClO3 produces 2 potassium chloride plus 3 oxygen gas. What is the total number of moles of potassium chlorate needed to produce 6 moles of oxygen? Okay, so I like to write out the numbers so I could see it. Okay, so we have 2 of potassium chlorate, and we're producing 2 potassium chloride and 3 oxygen gas. So now, how many moles of this do we need? So this is what we're looking for, to produce 6 moles of oxygen. So to get 6 moles of oxygen, how do we get from 3 to 6? We multiply by 2. So multiply your 2 here by 2, and you would need 4 moles of potassium chlorate. Okay, and you can keep going. They didn't ask us this, but then you would also produce, you would multiply this by 2, 4 moles of potassium chloride. Okay, so the ratio has to be the same throughout the formula to keep the mass conserved within the equation. Okay, if you want to set it up as a proportion here, you would say we have 2 moles of potassium chlorate, which produces 3 moles of oxygen gas. So now we want to see how many moles we would get of potassium chlorate to get 6 moles of oxygen. Okay, cross multiply. So 2 times 6 is 12 equals 3 times x, 3x. Divide it out, and 12 divided by 3 is 4. So 4 is x, which x was how much potassium chlorate. So 4 moles of potassium chlorate. Make a drawing of 6 molecules of hydrogen gas in a container and use a different symbol to add the correct number of nitrogen gas molecules to form ammonia according to the following equation. Okay, so 6 molecules of hydrogen gas. So start over here. Remember, hydrogen gas, it says that we have 3 hydrogen gas molecules, and we have a diatomic element here, right? So we have 3 H2s. And then it says, using a different symbol, add the correct number of nitrogen gas molecules to form ammonia according to the following equation. Okay, so here it says that we've got N2. So we're going to use, for nitrogen, an open circle. And this is getting into balancing. So if we have 2 nitrogens on this side, and on this side we have 2 nitrogens, so we're good. And here we have 6 hydrogens, and here we have 2 times 3, 6 hydrogens. So we're balanced. Although we're balanced, this is saying that we want to have 6 molecules of hydrogen gas. In our formula, we have 3 molecules of hydrogen gas. So if we have 6 hydrogens, okay, we need to add 3 more hydrogens to our container. So if we've got 6 hydrogens, 3 times 2 got us to 6. And here we had 1 mole of nitrogen. So if we multiply that by 2, right, times 2, we would need 2 moles of N2, of nitrogen gas, okay, to keep our ratio. So we need 1 more. Okay, and now we are producing, we have to adjust this because we doubled these, so 3 times 2 and 1 times 2, so we also have to multiply this part by 2. So we would have 4 molecules of ammonia produced. Okay, so now we're going to show the production of our ammonia. This is the particle drawing here. So now we have 4 NH3. So we have nitrogen with 3 hydrogens. Kind of look like little flowers. We can see that our beginning number of moles of nitrogen and hydrogen, if you count them up, we had 2, 4, 6, 8, 10, 12 hydrogens. We can see here we've got 3, 6, 9, 12 hydrogens. And we started with 4 atoms of nitrogen, and we have 1, 2, 3, 4 atoms of nitrogen. So our equation is balanced, our mass has been conserved, and we have done it properly. And that completes our notes for today, and see you next time.